Imagine this. You finally get a reply from a company after weeks of applications. They don't ask for DSA, they don't ask for theory. They send you a business case, a CSV file, 600,000 rows, 10 columns, and one line that says, build a fraud detection model and present actionable insights. Sounds exciting, right? And also slightly terrifying. This is where most data science candidates mess up. They immediately jump into coding, they open Jupyter, they import pandas, sklearn, XGBoost, and 3 hours later they have a model with 99% accuracy. But no story, no business reasoning, no clarity on why they did what they did. And the interviewer, they don't care about your ROC curve yet. They are asking one silent question. Does this person think like a data scientist or just like a coder? In this video, I am going to give you a practical end-to-end demo of how to approach a real data science interview assignment, exactly the kind you will get for analyst, data science or ML roles. Not a Kaggle style solution, not a notebook dump, but a structured interview ready approach that shows how you think, how you make decisions, how you connect data to business impact. The assignment we are working with today is a fraud detection problem for a financial company. You are given a CSV dataset with over 6 lakh transactions, a clear business objective, predict fraudulent transactions, and a list of expectations, data cleaning, model selection, evaluation, interpretation, and prevention strategy. This is not just a modeling task, it's a decision making exercise. And here's the most important mindset shift I want you to make. This is not a machine learning problem first, this is a business problem first. Your job is not to impress the interviewer with complexity. Your job is to convince them that you understand the business risk, you respect data limitations, and you can turn insights into action. So, in this demo, I'll walk you through exactly how I would explain my approach in an interview, step by step. First, how I read the problem statement and extract hidden expectations. Second, how I explore and clean the data with intent, not blindly. How I choose features and models based on interpretability versus performance. Fourth, how I evaluate the model using the right metrics for fraud. And fifth, and finally, how I translate the model output into real prevention strategies a company could actually implement. This is the difference between getting shortlisted and getting the offer. I will be working in Jupyter Notebook, but I will constantly pause to explain what I say out loud in an interview, how I justify decisions, and how to handle follow up questions from a hiring manager or senior data scientist. If you are a student, a fresher, or someone transitioning into data science, this is how you stand out, not by chasing the perfect model, but by telling a clear, confident story with your data. So grab a notebook, not just laptop, and think like an interviewer. Alright, so before we jump into the notebook or start writing any code, let's take a step back and frame the problem properly, because this is exactly what interviewers expect you to do. The business case we are given is a fraud detection problem for a financial service company. Now, on the surface, this might sound like a straightforward machine learning task: build a model, predict fraud, show accuracy, done. But in reality, it's much deeper than that. What we're essentially trying to do is help the company protect its revenue, its customers, its trust. Every fraudulent transaction that slips through means direct financial loss, but at the same time, every genuine transaction that gets blocked creates customer frustration. So, our objective is not just prediction, it's balance. In simple terms, yes, the technical goal is to classify whether a transaction is fraudulent or legitimate. But from a business lens, the success criteria looks like this. We want to maximize fraud detection, meaning we want to catch as many fraudulent transactions as possible while also minimizing false alarms so genuine customers are not unnecessarily blocked, delayed, or investigated. Because too many false positives can hurt customer experience and too many false negatives can hurt the company financially. So, the real question we are solving is how can we build a system that is accurate, reliable, and actionable in a real financial environment? That means our approach going forward will not just focus on model performance but also on interpretability, operational usability, and risk impact. Now that we are aligned on the business objective and success criteria, let's move into understanding the dataset we have been given. Now that we are clear on the business objective, the next step is to actually understand the dataset we have been given. Because in any data science interview assignment, how well you read the data often matters more than how fast you model it. So I have loaded the CSV into my notebook, and the first thing I want you to look at is the overall structure. We are working with a transaction level dataset that contains hundreds of thousands of rows, meaning each row represents a single financial transaction, and we have multiple columns describing transaction behavior, account balances, and transfer details. Now, let's identify the most important column first, the target variable, which in this case is fraud. This is a binary level. 1 means transaction is fraudulent, 0 means it's legitimate. So our entire modeling task will resolve around predicting this column accurately. Next, looking at the feature types, we have a mix of variables, categorical, type, payment, transfer, cash out, etc. Numerical, amount, balances before and after transaction, time or sequence based, step, which refers to 1, which represents the transaction timestamp, entry identifiers, name ORIG and name DEST are the customer accounts. This balance features like old balance org and new balance org interesting because sudden drops or zero balances can signal suspicious activity. Now, one critical thing always check early in fraud datasets is class imbalance. Typically, fraudulent transactions make up a very small percentage of the data, sometimes less than 1%, and that changes how we evaluate models. Because if 99% of transactions are genuine, the model can get 99% accuracy by predicting not fraud every time, which is useless. So instead of accuracy, we'll focus on recall how many frauds we correctly catch, precision, how many flag frauds are actually fraud, F1 score, balance between the two. Understanding this imbalance early helps us design the right modeling and evaluation strategy going forward. Alright, so let's start by setting up our environment for the fraud detection project, and I will walk you through every line so you can understand not just what we are importing but why we are importing it. First, I am importing OS. This library helps us interact with operating system, for example, reading file paths or managing dictionaries if needed later. Next, I am importing warning and then write warnings.filter warnings ignore. This simply surpasses unnecessary warning messages in the notebook so our output stays clean and presentation friendly, especially during demos or interviews. Then I am importing display from ipython.display. This allows me to render datasets, tables, or slate outputs more clearly inside Jupyter. Moving on to our core data libraries, I import NumPy as NP and Pandas as PD. NumPy handles numerical computations, while Pandas is our primary tool for loading, cleaning, and analyzing tabular data like this transaction dataset. For visualization, I import matplotlib.pyplot as PLT, which we'll use later for EDA charts like fraud distribution and transaction patterns. Now entering the machine learning section, from sklearn.model selection, I import train test split. This will help us divide the data into training and testing sets. From preprocessing, I import robust scaler for scaling numerical features, especially useful when outliers exist, and label encoder to convert categorical variables into numeric forms. Next, evaluation metrics, classification report, confusion metrics, ROC, AUC score, and precision recall metrics. These are critical because fraud detection relies heavily on recall and precision, not just accuracy. For modeling, I import two algorithms. First, logistic regression, a baseline interpretable model. Second is random forest classifier, a powerful, a simpler model. I also attempt to import XGBoost. If it is not installed, I safely set it to none so that the notebook doesn't crash. Finally, I import joblib to save the trained models and print setup complete to confirm everything loaded successfully. Now our environment is ready to start working with the data. Alright, now that our environment setup is complete, the next step is to actually load the dataset we'll be working with. So the first line here, data path equals to data.csv, is where I define the file location of my dataset. Instead of hardcoding the path multiple times, I store it into a variable. This makes the code cleaner and easier to manage if the file location changes later. Next, I use a assertion check. Assert os.path.exist data path, comma, dataset not found. What this does is verify whether the dataset actually exists in the specified path. If the file is missing, the code will immediately stop and show the message dataset not found. This is a good practice in interview assignments because it prevents silent error and shows that you are writing defensive production ready code. Now that we have confirmed the file exists, I load it using pandas df equal to pd.read csv data path. This line reads the CSV file and stores it inside a data frame called df. You can think of a data frame as an Excel sheet inside Python, rows and columns that we can analyze programmatically. Finally, I run df.head. This displays the first 5 rows of the dataset so we can quickly preview the structure without loading the entire table on screen. From this preview, we can already observe several important things. We have transaction timestamps under step, transaction categories under type like payment, transfer, and cash out, and transaction amounts in the amount column. We also see sender and receiver account IDs, name ORIG, and name DEST, along with their balances before and after the transaction. Most importantly, we see our target variable is fraud and an additional flag column is flagged fraud. This quick preview helps us validate that the dataset loaded correctly and gives us an initial understanding before deeper exploration. Alright, so now that our dataset is loaded, let's do some quick exploratory data analysis. This is what I call the health check of the data before we start modeling. The first line I run is print shape df.shape. This tells me the size of the dataset, number of rows and columns, and we can see that the dataset contains around 6 lakh rows and 11 columns. So we are working with a fairly large real world scale transaction dataset. This is a great for learning and building a robust fraud detection model. Next, I check the data types using print df.types. This helps me understand what kind of variables we are dealing with. For example, type, name ORIG and name DEST are objects or categorical variables. Transaction balances and amounts are float values. Fraud labels like is fraud and is flagged fraud are integer binary variables. Understanding data types early is important because it tells us what encoding or pre-processing will be required later. Now, the next step is checking for missing values. Print df is null.sum, and from the output we can see that there are 0 null values across all columns. This is actually rare in real world datasets and it simplifies our preprocessing since we don't need imputation strategies here. Next, I look at the class distribution. Print df is fraud.value counts. This shows how many fraudulent versus legitimate transactions we have. We can see that legitimate transactions are over 6.35 million and fraudulent transactions are only around 8,200. Finally, I calculate the fraud ratio. Print fraud ratio df is fraud.mean, which comes out to roughly around 0.13%. This confirms that a heavily imbalanced dataset, which is expected in fraud detection. And this is exactly why accuracy alone would be misleading. So later we will focus more on recall, precision, and F1 score when evaluating our models. Alright, so now let's move into a slightly deeper analysis. And here's I want to understand one very important question. Does transaction amount influence fraud probability? Because intuitively, higher value transactions often carry higher fraud risk, but we want to validate this with data. So let's walk through this code step by step. First line df amount bin equals to pd.qcut df amount comma q equals to 10 duplicates equal to drop. What I am doing here is creating transaction amount buckets. Qcut splits the amount column into 10 equal quantiles, meaning each bucket contains roughly the same amount of transactions. This is better than fixed ranges because it balances the data distribution. The duplicates equal to drop parameter ensures that if some bucket edges repeat due to identical values, pandas safely handle it without errors. So now we have converted a continuous variable amount into a grouped range like low, medium, high value transactions. Next, fraud rate equals to df.group by amount bin is fraud.min. Here I am grouping the data by these amount buckets and calculating the average fraud rate in each bucket. Since each fraud is binary 0 or 1, that means directly represents the fraud probability. Then fraud rate equals to fraud rate into 100. This simply converts the values into percentage so they are easier to interpret visually. Now for visualization, plt.figure figure size equal to 10, 4. This defines the chart size so labels are readable. Fraud rate dot plot kind equals to bar. This creates a bar chart showing fraud rate across amount buckets. Then I label the axis and add a title. Y-axis equals to fraud rate, title equals to fraud rate by transaction amount bucket. Finally, plt.show renders the plot. And the insight here is powerful. We observe that fraud rates increase significantly in higher value transactions amount buckets. So, transaction amount is not just a magnitude feature, it's a strong risk indicator. This tells us that high value transactions should receive stricter fraud monitoring or additional verification layers in real world systems. Alright, so the next step in our exploratory analysis is to investigate missing values and data validity because in financial datasets, what looks like missing data is sometimes actually meaningful behavior. So first I run df is null.sum. This line checks for null or missing values across every column in the dataset, and from the output we can see that there are no missing values at all. Now at first glance this looks perfect, but in fraud datasets we have to be careful because sometimes values are filled with zeros instead of being left blank. So I dig a little deeper. Here, I specifically investigated merchant transactions. To do that, I filtered rows where the destination amount starts with letter M. Merchant transactions equal to df names dest dot str dot starts with M. In this dataset, accounts starting with M represent merchant accounts, meaning payments made to business rather than individuals. Next, I analyze the destination balances for these merchant transactions. Merchant transactions old balance DEST, comma new balance DEST dot describe. This gives me summary statistics, count, mean, standard deviation, mean, max, etc. And the result is interesting. All the balance values are 0, mean 0, standard deviation 0, mean max 0. So initially, This might look like missing or corrupted data, but it's actually not. This is expected behavior in this dataset because merchant accounts don't maintain tracked balances the same way customers' wallets do. So zeros here are structural variables values, not missing values. And this leads to an important pre-processing decision. We do not perform imputation on these fields because replacing these zeros with average or medians would introduce fault transaction behavior into the data. So the takeaway from this step is there are no true missing values. The zero balance in merchant transaction represent valid system design, not data quality issues. Understanding this nuisance is crucial in fraud analytics before moving into modeling. Alright, so now let's talk about outline analysis, specifically focusing on the transaction amount feature. Because in fraud detection, outliners are not always noise. Sometimes they are actually the fraud signals we are trying to detect. So the first line I run is df amount.describe. This gives me a summary statistics for the transaction amounts, things like minimum value, maximum value, mean, and typically in financial transaction datasets, what we observe is a massive gap between the median transaction and the maximum transaction value. That gap immediately tells us that the data is highly skewed, meaning most transactions are small but a few are extremely large. To visualize this skewness, I plot a histogram df.figure figure size 7,4. This just sets the chart size for better readability. Next, plt.hist df amount, bins equals to 100. Here I am plotting the distribution of transaction amounts across 100 bins. This gives a granular view of how transaction values are spread. Because if we plot this on a normal scale, the smaller transactions dominate the charts and we can barely see the high value ones. So I apply a log transformation on the y-axis, plt.yscale log. This compresses the frequency scale and allows us to visualize both low and high transaction volumes clearly. Then I label the axis, x-axis for transaction amount, y-axis for frequency on log scale, and add the title transaction amount distribution highly skewed. From this visualization, we can clearly observe a long right tail, meaning a small number of transactions involve a very high amounts. But now in many machine learning problems, we might cap or remove outliners. But in fraud detection, removing high value transaction could mean removing fraud itself. So instead of deleting them, we typically handle skewness using techniques like scaling or log transformation during pre-processing. Alright, so after identifying that the transaction amount distribution is highly skewed, the next step is to handle that skewness in a way that improves model learning without losing fraud signals. So the first technique I apply is a log transformation. Here's the line df log amount equals to np.log 1p df amount. What this does is that it creates a new feature called log amount. Instead of using a raw transaction value, we apply the natural log transformation using log 1p. Now, you might wonder why log 1p and not just log. That's because log 1px computes log 1 plus x, which safely handles zero value transactions without causing mathematical errors. The benefit of this transformation is that it compresses extreme values, bringing very large transactions closer in scale to smaller ones, while still preserving their relative differences. This makes the data more model friendly, especially for linear algorithms. Next, I create a behavioral risk flag for very large transactions. First, I calculate the 99 percentile threshold P99 equals to df amount dot quantile 0.99. This gives me the cutoff value above which the top 1% highest transactions lie. Then I create a binary flag df is high amount equals to df amount greater than p99 dot as type int. So if a transaction amount exceeds the 99 percentile, it flags 1 or otherwise 0. Finally, I check the distribution. df is high amount dot value counts, and we can see that roughly around 63,627 transactions fall into the high value category, about 1% of the dataset. This feature is extremely useful because it explicitly captures extreme value behavior. So instead of removing outliers, we preserve them and even highlight them. In fraud detection, these high amount spikes often strongly associate with fraudulent activity, making this engineered feature a valuable risk indicator while retaining all original data. Alright, so now let's take a step back from feature engineering and look at the high level fraud overview, because before building any model, we need to understand the scale of the problem we are solving. So first I calculate the total number of transactions. Total transactions equals to length df. This calculates counts all rows in the dataset, and we can see we are working with around 6.36 million transactions. Next I calculate how many of these are actually fraudulent transactions. Fraud transactions equals to df is fraud dot sum. Since fraud is labeled as 1, summing the columns gives the total fraud count, which is around 8,213 transactions. Now to compute the fraud rate equals to fraud transactions divided by total transactions. And I also convert it into percentage, reporting clarity. For the output, we see the overall fraud rate is around 0.13%, which confirms this is an extremely imbalanced dataset. But here's where it gets interesting. I also calculate how many transactions were flagged by the existing rule-based system. Flagged PCT equals to DF is flagged fraud dot sum divided by total transactions into 100. And the result is shocking. Only about 0.0003% of the transactions are flagged. So while 0.13% are actually fraudulent, the current system flags almost none of them. This gap clearly indicates that most fraudulent activity is going undetected, which strongly motivates the need for machine learning driven detection system. Next, I analyze the fraud behavior by transaction type. df.group by type is fraud.mean. This calculates the fraud rate within each transaction category like payment, transfer, cash out, etc. Then I sort and visualize it using a bar chart. This helps us identify which transactions type carry the highest fraud risk. Typically, fraud is concentrated in transfer and cash out operations where money is being moved or withdrawn rather than simple payments. These insights are critical because they guide both feature engineering and real world fraud prevention strategies. Alright, so now let's move into time based fraud analysis, because fraud is not just about who or how much, it's about when. And time pattern often reveals behavioral anomalies that models can learn from. So first I create an hour of the day feature using this line df hour equals to df step divided by 24. Now in this dataset, step represents time in sequential hours from the start of the simulation. By taking modulus 24, I convert it into a standard hour of the day format, values from 0 to 23, which allows us to analyze daily transaction behavior. Next, I aggregate hourly statistics. Here I group the dataset by hour and compute three metrics: total transactions, fraud transactions, and fraud rate. This gives me a summarized hourly view of both activity and risk. Display hourly stats.head just previews the first few rows so we can validate the aggregation. Now let's visualize fraud risk by hour. I plot a bar chart where x-axis hour of the day, y-axis fraud rate. This helps us see whether fraud spikes at specific times, for example, late night or early morning, when monitoring is typically lower. Then I analyze transaction volume patterns using a line plot. I show how many transactions occur each hour. This is important because high fraud rate during low volume transaction hours can signal targeted attacks rather than random behavior. Finally, I create a day versus night fraud comparison. First, I define night hours. DF is night equals to DF hour dot is in 0 to 5, 22, 23. This represents late night low supervision windows. Then I calculate the fraud rate for day versus night and visualize it using a pie chart. This analysis helps answer a strategic question: is fraud evenly distributed or time targeted? And if night hours show higher fraud concentration, financial institutions can implement stricter verification, velocity checks, or transaction monitoring during these windows. Alright, so now let's move into correlation analysis because before training any machine learning model, it's important to understand how our numerical features relate to each other. High correlation between variables can lead to multicollinearity, which negatively affects model stability, especially for linear models like logistic regression. So first I import visualization libraries like import matplotlib.pyplot as PLT, import seaborn as SNS. Matplotlib handles base plotting while seaborn helps create more advanced statistical analysis visuals like heat maps. Next, I define the plot size plt.figure figure size equal to 10,7. This just ensures that the heat map is large enough to read clearly during the demo or presentation. Now I compute the correlation matrix CORR equals to TF old balance ORG, new balance ORIG, old balance DST, new balance DST, amount dot CORR. Here I am selecting key financial features balances before and after the transaction for both sender and receiver along with transaction amount. The dot CORR function calculates pairwise correlation coefficients ranging from -1 to +1. Then I visualize it sns.heatmap CORR, anode equals to true, CMAP equals to cool warm, FMT equals to dot 2F. Anode equals to true displays the correlation values inside each cell. Cool warm color palette highlights the positive versus negative relationship. FMT equals to dot 2F limits values to two decimal places for readability. I also add a title and display the chart. Now the insights here is very important. We observe strong correlation between pre and post transaction balances. For example, old balance ORG versus new balance ORIG, old balance DST versus new balance DST. This indicates redundancy because post transaction balance is mathematically derived from pre balance and transaction amount. So keeping all these variables can introduce multicollinearity. To address this, instead of using redundant new balances, we engineered the balance difference features. This reduces feature overlap, introduces model interpretability, and ensures numerical stability during training. Alright, so now we are entering one of the most important stages of the pipeline, feature engineering and data cleaning. This is where raw transactional data gets transformed into meaningful signals that machine learning models can actually learn from. So first I create balance difference features. Here's the first line. df balance difference ORIG equals to df old balance ORG minus df new balance ORIG. This calculates how much balance was reduced from the sender's account during the transaction. Instead of giving the model two highly correlated variables, old and new balance, we give it the actual transactional impact. Similarly, for the receiver, df balance difference DEST equals to df new balance DEST minus df old balance DEST. This captures how much balance was added to the destination account. These engineered features are more interpretable and reduce redundancy. Next comes feature reduction. Since we have extracted the useful signal, we no longer need the original balance columns, so I drop them. df equals to df.drop columns, old balance org, new balance org, old balance dest, new balance dest. This helps reduce multicollinearity and simplifies the dataset, which is especially beneficial for linear models like logistic regression. I also removed the earlier amount bucket feature df.drop columns equal to amount bin in place equals to true. Since it was mainly used for EDA visualization, it is not required for modeling. Next, I handle any residual missing values df.fill na 0 in place equals to true. Even though we didn't observe null earlier, this acts as a safety step for production robustness. Now I encode categorical transaction types using label encoder. LE equals to label encoder, df type enc equals to le.fit transform, df type. This convert categories like payment, transfer, cash out into numeric labels that model can process. Finally, I drop non-informative identifiers df.drop name ORIG, name DEST, type, access equals to 1, in place equals to true. Account IDs don't generalize patterns, they just add noise, so removing them keeps the model focused on behavioral signals rather than entity specific data. Alright, now that our features are engineered and the dataset is clean, the next step is to prepare the data for model training, starting with the train test split and feature scaling. So first I separated the input features and the target variable. X equals to df.drop columns equals to is flagged fraud. Here X contains all predictor variables, everything that model will use to learn patterns. I remove is fraud because that's the label we are trying to predict, and I also drop is flag fraud since it's an existing rule based flag that could leak information into the model. Then I define the target y equals to df is fraud dot values. This stores the fraud label as a numpy array for modeling. Next comes the 10 test split. Extend x test y test equals to train test split x comma y test size equals to 0.2 stratify equals to y random set equals to 42. So I am splitting the data into two 80% training data, 20% testing data. The key parameter here is stratify equals to y. Because fraud data is highly imbalanced, stratification ensures that both train and test sets maintain the same fraud portion as the original dataset. Without this, we might end up with few fraud cases in the testing, leading to unreliable evaluation. Random set equals to 42 ensures reproducibility, meaning the splits remain consistent every time we run the code. Now we move to feature scaling. I use scalar equals to robust scalar. Unlike standard scalar, robust scalar is resistant to outliers, which is ideal for transaction data with extreme values. Next, I identify numerical columns. Num columns equal to xtrain dot select d types include np dot number dot columns. Then I fit the scalar only on training data. Scalar dot fit xtrain num column. This avoids data leakage from the test set. Finally, I transform both train and test features. Xtrain num columns equal to scalar dot transform. Xtrain num columns. Xtest num columns equal to scalar dot transform. Xtest num columns. Now the dataset is properly split and scaled, ready for model training. Alright, now we have reached the most anticipated stage of the pipeline model training and evaluation. Here, the goal is not just to train one model, but to compare multiple algorithms and see which one handles fraud detection best. So, first, I create an empty dictionary models. This is just a container where I will store all the training models for later evaluation and comparison. Logistic regression. I start with baseline model, print training logistic regression. Then I initialize logistic regression with a few important configurations. Max iter equals to 300 limits training iterations for faster convergence. Solver equals to LBFGS efficient optimization algorithm. Class weight equals to balance, very important. It automatically adjusts weights to handle class imbalance. Njobs equals to -1 uses all CPU cores for faster processing. Then I train the model lr.fit xtrain, ytrain. Once trained, I store it. Models logistic regression equals to lr. This baseline gives us interpretability and performance reference. Random forest. Next I move to an assembler model print training random forest. Here I optimize the speed and overfitting controls. N estimators equals to 50, number of trees reduced for faster training, max depth equals to 12, prevents overly deep trees, minimum sample leaf equals to 100, avoids tiny leaf splits, class weight equals to balance, again handles fraud imbalance, njobs equals to -1 for parallel processing. Then I fit and store the model. Random forest captures nonlinear fraud patterns much better than logistic regression. XGBoost. Finally, I train XGBoost. I first compute class imbalance weight scale pos equals to ytrain equal to 0 dot sum divided by ytrain equal to 1 dot sum. This tells XGBoost how much more important fraud cases are. Then I configure the model n estimators equals to 100, max depth equals to 6, learning rate equals to 0.1, subsampling for generalization, tree method equals to hist for faster training. After fitting, I store it in the models dictionary. So now we have three trained models logistic regression, random forest, and XGBoost ready for performance evaluation and comparison. Alright, now that all the three models are trained, the next step is to evaluate and compare their performance, and this is where fraud detection gets really interesting. So I start by creating an empty list results. This will store evaluation metrics for each model so we can compare them side by side later. Next, I loop through every trained model for name, model in models.items. This allows me to evaluate logistic regression, random forest and XGBoost using the same pipeline. Now inside the loop, I generate prediction score, not just class labels. If has at a model predict probability scores equals to model dot predict probability x test, else score equal to model dot decision function x test. If the model supports probability prediction, I extract the fraud probability. If not, I use the decision score instead. This is important because metrics like ROC AUC and PR AUC requires probability score, not binary outputs. Then I print the classification report y test score greater than 0.5 as type int. Here I convert probabilities into class prediction using a 0.5% threshold. The report shows precision, recall and F1 score for both fraud and non-fraud cases. Now let's interpret the results. Logistic regression shows very high recall. It catches about 89% of fraud cases, but precision is extremely low at around 3%. This means it flags many genuine transactions as fraud. Random forest improves the balance. Recall rises to 96% and precision increases slightly, meaning fewer false alarms while still catching most frauds. XGBoost performs similarly in recall but with strong probability ranking. So to compare the ranking ability, I compute ROC AUC score, average precision score, PR AUC. This gets appended into the result list and converted into a data frame. And this is the key insight. While all models achieve very high ROC-AUC, the PRAUC, which is more meaningful for imbalanced datasets, shows XGBoost clearly outperforming the others. This indicates it significantly better at identifying rare fraud cases. So, from a development perspective, XGBoost becomes the strongest candidate for a production fraud detection system. Alright, this is a very important interview grade step, tuning the decision threshold. Most candidates completely miss this, so explaining it clearly really sets you apart. Up until now, our model has been predicting fraud probabilities, not hard yes or no decisions. So the first thing I do is select the best performing model, which is our case is XGBoost. Model equal to models XGBoost. Now I generate fraud probability score on the test data. Y score equals to model.predict probability x test. This gives me a value between 0 and 1 for each transaction essentially. How confident the model is that this transaction is fraudulent. Next I compute the precision recall curve. Precision recall threshold equals to precision recall curve y test y scores. This is crucial for imbalance problems like fraud detection. Instead of fixing the threshold at 0.5, this curve shows how precision and recall changes at different probability cutoffs. Now comes the business driven part. I define my constraint. I want to catch at least 90% of all frauds. So I filter threshold recall is greater than or equal to 0.90. Candidates equal to TPR for TPR in zip thresholds precision -1 recall -1. If R greater than 0.90 means 90% greater than 90%. For those candidates, I select the threshold that gives the highest precision. Best threshold, best P, best R equals to max candidates, key equals to lambda x 1. This means we maintain high fraud coverage while minimizing false positives. Now let's interpret the results. The best threshold comes out to be around 0.91. This means that the system will only flag a transaction if the model is more than 91% confident that it's fraudulent. At this threshold, recall equals to 90%. We catch most frauds when precision is around 35%. Far fewer genuine transactions are flagged. This is a huge operational improvement. Instead of overwhelmingly investigators with fraud alerts, we reduced review volume while still protecting revenue. And this is exactly how fraud models are deployed in real world, not with a fixed 0.5 threshold, but with a threshold aligned to business risk and cost. This is the difference between a good model and a usable system. Alright, now that the baseline models are trained and evaluated, the next step is to fine tune them to improve the fraud detection performance because default parameters rarely give the best results, especially in highly imbalanced problems like fraud detection. So I start by redefining each model with optimized hyperparameters. XGBoost fine tuning. First I tune XGBoost since it was already the best performing model. Now let's understand the tuning decisions. N estimators equals to 200. I increase the number of trees so that the model can learn more complex fault patterns. More trees, better learning, but controlled with other parameters to avoid overfitting. Max depth equals to 4. This restricts how deep each tree can grow. Fraud datasets are noisy. Deep trees memorizes noise, so shallower trees generalizes better. Learning rate equals to 0.005. I reduce the learning rate so boosting happens more gradually. Lower learning rate plus more trees equal to better stability and precision. Subsample and goal sample by tree equal to 0.8. This introduces randomness 80% of rows sampled per tree, 80% of features sampled per tree. This reduces overfitting and improves generalization. Mean child weight equals to 50. This is critical for imbalanced data. It forces the model to create splits only when there's enough fraud signal. So it prevents the model from chasing tiny fraud noise patterns. Scale pause weight. This handles class imbalance directly. Since fraud cases are rare, I weight them higher so that the model pays more attention to them. Then I train the tuned model. XGB tuned.fit xtrain, ytrain. Random forest fine tuning. Next I tune the random forest. N estimators equals to 100. More trees improve stability and voting strength. Max depth equals to 10, limits trees growth to avoid memorizing majority class patterns. Mean sample leaf equals to 200. This has a huge impact on fraud precision. Each leaf must contain at least 200 samples, preventing tiny fraud only leaves that cause false positives. Mean sample spread equals to 500, forces splits only when enough data exists, again helps reduce noise-based splits. Class weight equals to balance, automatically weights fraud cases higher to handle imbalance. Then I train it, rf tune.fit, x train, y train, logistic regression fine tuning. Finally, I tune logistic regression. Class weight equals to balance ensures fraud cases influence the decision boundary more. C equals to 0.3. This controls regularization strength. Lower C refers to stronger regularization, which refers to simpler model. This helps prevent overfitting and reduce false fraud flags. Then I train it. LR tune.fit x train, y train. So the big picture interpretation is our overall fine tuning focuses on three goals. First, handling class imbalance, scales pause weight, class weight, reducing overfitting, max depth, mean child weight, and meal sample leaf. Third is improving the fraud precision, regularization, control splits, and subsampling. In short, baseline models learn fraud patterns, fine tuning models learn them more carefully, more robustly, and with few false alarms, making them far more suitable for real world development. Alright, now we move into the final performance validation stage, evaluating the fine tuned models. At this point, all three models have already been optimized with better hyperparameters, so the goal here is simple not to retrain but to measure how well each tuned model ranks fraud risk. So first I import the evaluation metrics from sklearn.metrics import ROC AUC score average precision score. These two metrics are crucial in fraud detection. ROC AUC measures the overall ranking ability. PR AUC, more important for imbalanced dataset, focuses on fraud detection quality. Creating an evaluation function instead of repeating code for every model, I defined a reusable function. Let's break it down. First, I generate the fraud probability scores. Scores equals to model dot predict probability x1. This extracts the probability of the fraud class. Class equals to 1. We use probabilities, not labels, because AUC metrics evaluate ranking quality. Then I compute ROC AUC score, Y scores, average precision score, Y scores, and return them as a dictionary for each for easy comparison. Evaluating each tuned model. Now I run the function on all three models. This prints the performance metrics side by side. In XGBoost, ROC AUC score is around 0.99 and PR AUC score is around 0.86. This is the strongest performer. A PR AUC of 0.86 means it's highly effective at ranking fraud transactions above genuine ones, so it catches most frauds while keeping false alerts relatively low. Random forest ROC AUC score is around 0.997 and PR AUC is around 0.83, very close to XGBoost but slightly weaker in fraud precision recall balance. It still performs excellent but ranks fraud risk at a bit less sharply. Logistic regression. ROC AUC score is around 0.977 and PR AUC is around 0.55. This is significantly lower, especially PRAUC. It struggles to separate rare fraud cases from normal transaction, which is expected since linear models cannot capture complex fraud patterns. What we can see here is that the most important takeaway is all models show very high ROC AUC, but PR AUC reveals the real story. Because fraud detection is highly imbalanced, PR AUC is the more realistic metric, and because of that, XGBoost is the best fraud ranking ability, random forest strong second, and logistic regression is the baseline only. From a development perspective, so if we are developing, XGBoost would be the top choice. It catches the highest proportion of fraud cases while minimizing false alarms, making it operationally efficient for fraud investigation teams. Alright, now we have reached the model, packaging, and development preparation stage. This step is extremely important because training alone isn't enough. We need to save the best performing model so it can be reused later without retraining. So first I create a dictionary containing all the fine-tuned models. Models equals to logistic regression, LR tune, random forest, RF tune, and XGBoost, XGB tune. This acts as a lookup table where each model name maps to the trained object. It makes selection and retrieval easier. Selecting the best model. Next, I automatically identify the top performer, best model name, max results, key equal to lambda x AUPRC model. Here's what happening here is that I loop through the result list which contains the evaluation metrics. I compare the model based on PRAUC, the most relevant metric for imbalance fraud detection. Max returns the model with the highest PRAUC score so that the system objectively picks the best model, no manual bias. Then I retrieve the actual trained model object. Best model equals to models, best model name. Now I have the winning model ready for packaging. Creating the model artifact. Instead of saving just the model, I bundle everything required for real world inference. Let's unpack this. Model name identifies which algorithm was selected. Model refers to the trained model object. Threshold refers to the optimized decision cutoff, which is around 0.91. And features refer to the extracted feature list used during training. Saving features is crucial. It ensures future input data matches the training schema. Saving the model. Now I serialize the artifact using joblib. Joblib.dump best model artifact best fraud model tune.pkl. This creates a .pkl file containing the full development package so later we can load it instantly without retraining. The final output is the saved model is saved as XGBoost and decision threshold is around 0.9084. This confirms that XGBoost achieved the best PRAUC. Fraud prediction will only trigger if probability is greater than 0.9084. This high threshold ensures that around 90% fraud recall, much lower false positives, and reduced investigation cost. At this point, the fraud detection pipeline is production ready. Data pre-processing is defined, features engineered, model trained and tuned, threshold is optimized, best model packaged and saved, so that the system can now be integrated into the banking transaction monitoring system, real-time payment gateways, or fraud alert dashboards. Alright, now comes the moment of truth model testing on real data. We have trained, tuned, and saved the best fraud detection model, but the real question is how does it perform in practice? So let's walk through the testing pipeline step by step. First, I load the saved model artifact. Artifact equals to joblib.load best fraud model tune.pkl. Remember, this isn't just the model, it contains the trained algorithm, the optimized fraud threshold, the exact feature list used during training. Next, I extract the components model equals to artifact model, threshold equals to artifact threshold, features equals to artifact features. This ensures productions uses the same structure that the model expects. Consistency is crucial in fraud systems. Even one missing feature can break predictions. Generating fraud scores. Now I generate fraud probabilities. Y score equals to model.predict probability. X test features 1. Instead of predicting 0 or 1 directly, the model outputs fraud probability scores. This gives flexibility to apply a custom decision threshold. Applying the optimized threshold. Y predict equals to Y score greater than equals to threshold dot as type int. Here's the key difference from the default ML pipelines. We are not using a 0.5%. We are using the tune threshold which is around 0.9084. So a transaction is flagged only if fraud probability exceeds 90.84%. This dramatically reduces false alarms. Confusion matrix breakdown. Next, I compute the confusion matrix TNFP FNTP equals to CM dot rival, and it summarizes the values at TF is around 1474, missed fraud, false alarms, and correct non fraud. Let's interpret what is going on. Fraud recall is around 0.897, which is around 90%. So the system catches around 9 out of every 10 fraud cases. That extremely strong fraud capture. Fraud precision 0.290, which is around 29%, meaning roughly 1 in 3 flag transaction is actually fraud, and in fraud detection, that's a solid operational ratio. Because the goal is to reduce investigator workload while still catching fraud. Operational impact. Let's translate this into business terms. 1.27 million legitimate transactions passed safely. Only 3,600 alerts raised for review, just 169 fraud cases missed. This is a massive efficiency gain. Legacy rule systems typically generate tens of thousands of false alerts. This ML system cuts that noise drastically. Why this matters? Because fewer false alarms means lower investigation cost, faster review cycles, less customer friction, higher trust in payment systems. At the same time, high recall ensures fraud losses stay controlled. Final insights. So at the optimized threshold is around 90% fraud recall, 29% precision, minimal missed fraud, massive legitimate transaction clearance. That's a huge operational improvement, and this is exactly why threshold tuning plus ML models like XGBoost are game changers in modern fraud detection system. Alright, now let's move into the final and the most important part of any data science interview assignment, answering the business and the modeling questions. This is where you prove you're not just coding, you're thinking like a fraud analyst and a data scientist. Data cleaning. So, first, data cleaning. Interestingly, the dataset has no true missing values. At first glance, zero balances look suspicious, but after deeper analysis, I found that these zeros were actually valid, especially for merchant transactions where destination balances are not recorded. For skewed financial distributions, I applied a log transformation on transaction amount and also created a high amount flag to capture extreme value fraud behavior. Additionally, high correlated balance columns were redundant, so I engineered a balance difference features to represent money moment money momentum more effectively. Model building. Next, modeling. I framed this as a binary classification problem, fraud versus non fraud. I trained three models: logistic regression, random forest, XGBoost. After training and threshold tuning, XGBoost delivered the strongest performance, especially on imbalance fraud duration. Variable selection, feature selection combined, domain knowledge, amount, transaction type, time. Correlation analysis, engineered balance features, model feature importance. This ensures both statistical relevance and business interpretability. Performance. The tuned XGBoost model achieved around 90% fraud recall and 29% precision. PRAUC is around 0.88. So it captures most fraud while keeping false alerts operationally manageable. Key fraud predictors. Top fraud signals include large transaction amounts, sudden origin balance drops, nighttime activity, risky transaction types like transfer and cash outs, non merchant destinations. These align strongly with real world fraud behavior. Do these insights make sense? Absolutely. Fraudsters typically move large funds quickly, often at night, and route money through non merchant accounts to avoid traceability. Prevention measures. From a business perspective, this model can power real time ML scoring, setup authentication, velocity checks, two stage detection pipelines, continuous model retraining. Measuring effectiveness. Finally, success would be tracked using fraud caught versus missed, false positive rate, alert to fraud conversion, before versus after deployment metrics. And that closes the loop from raw data to real business impact.